Hello everyone, my name is Ivan Savu and I will be talking about high performance applications with VeloxDB. First, I'll tell you a couple of words about myself. As I mentioned, my name is Ivan Savu. I'm currently CTO at VeloxDB. We are building a high performance database and I will tell you a bit more about it later. My background is mostly in energy software. I have been working for 16 years at Schneider Electric, building software for utilities, mostly software that controls power distributions, basically electric distribution. And 2 years ago in 2022, I have left Schneider Electric and founded VeloxDB. So now I'm currently at a startup and I'm building a fast database. So I'd also like to mention I'm very interested in software correctness and high performance. So if you have anything about that, feel free to contact me and I'm always available either from my email or from my LinkedIn. So let's look at what this talk is going to be about. We are going to pick one problem and basically look at how to implement it in such way that it achieves good performance. We are focusing on ticketing problem, and we will also give a brief overview of VeloxDB so that we know a bit about the tool we are using to implement. We'll go over the implementation, how we tested the implementation, and a couple of takeaways. So, for start, a quote from Sun Tzu. If you know the enemy and know yourself, you need not fear the result of 100 battles. So, basically, two important things from a quote, which I believe still applies even 1,000 years after Sun Tzu. The first one is know your enemy. And by knowing your enemy, I mean when developing a software, you should do your best to understand the problem space. Like have a good definition of what you are building, and especially regarding performance. Like have good definition of what performance expectations you have. Often I have discussions with people building software, and when I ask them what kind of performance are you expecting, they say we used scale out tools and we built it from the start and we expect we can handle any performance. And it usually doesn't work like that. Like the second most important thing is understanding what loads do you expect with your system. Like how many users will access the system, how does the load look, are there peaks or is it all uniform, how long does the peak last, things like that. So you need to think about that and estimate and design for that. So the problem we are going to talk about is ticketing software, and it's an interesting problem because it has a couple of interesting challenges regarding performance and both correctness. The first one is ticketing works often with massive load surges. Like often you have a concert or some other popular event where you have a limited amount of tickets, 1,000, 10,000, maybe 100,000, and often a lot more people that are interested in acquiring these tickets. The ratio can be maybe 100 more people are interested into the tickets than the tickets that are available. And another interesting thing is because when there's such a high discrepancy between demand and supply, people usually charge the website. Basically, when you start selling the tickets, they will try to acquire everything in the next 15 minutes, and that creates huge load. But there are other challenges as well. Since you're selling, you have to be correct. Like you cannot afford yourself when selling tickets to do like a double booking, to sell one ticket to two different persons, or maybe like to allow someone to pay you to complete a transaction but doesn't get a ticket. So it has to be correct. There's also additional challenge of because tickets are often, because of their demand, are targeted of automated bots which are trying to acquire tickets alongside users. So a very interesting problem. And these challenges have been like have escalated for quite a long time. Like if you go into Google and search, you can find so many examples of crashes of ticketing software. So I have picked up 4 here. If I had time and will, I could have probably collected 100 of them. And the largest event I saw was Taylor Swift's Eras Tour. She was selling 2.4 million tickets and 40 million users showed up. The site crashed and lots of fun was had. So, and while I was researching previous examples of software crashes with ticketing, I came upon a very interesting tweet from Ticketmaster during Ed Sheeran's tour in 2017. Be patient, don't give up. Stay in the queue and don't refresh. And this don't refresh, that really struck a chord with me, because while I was working in energy industry, I had once a situation where we were doing factory testing with a load operator and software was misbehaving. We were having a lot of load issues, and from time to time the software would freeze. And what the load operator would do when the software freezes is he would start clicking a lot, like maniacally clicking on a button. And the software will, of course, collect everything, and when it becomes available, it will try to execute everything, making the problem 1,000 times worse. And once I asked him, can you please not click when it's frozen? And what he did is, like, he clicked 1,000 times more. Like, you mean not do this? And he clicked 100 times more. And of course, I was young then and I understood the lesson, like, this is what is going to happen in production. You cannot ask user not to be jumpy when his software is not behaving. So I'm not sure how effective this tweet was, but I'm expecting that it's not the right solution for the job. So these are requirements I have put in front of myself and for the software we are building today. I want to sell 100,000 tickets, and I want to support 50 million concurrent users. One ticket can only be sold to one user. All tickets should be sold, and users should be able to buy multiple tickets automatically. That means if a user wants to buy 3 tickets at the same time, it's not okay to sell them 2 tickets and the third to sell to someone else. Like, either the user gets all 3 tickets or none. Unfortunately, I did not implement this functionality because of time constraints, but it's a very important feature because it affects your database choice. And I'll come back to it a bit later. And of course, good user experience. Latency should be low. Like, for example, when I was reading about the Oasis crash, a lot of people complained that they were waiting for 4 hours in queue. And that's not something your users should be subjected to. Like, there are not many tickets and there is no reason to wait 4 hours in a queue to find out that there are no more tickets. So the second part of Sun Tzu quote is know yourself. And by that, I mean know your tools well. By knowing your tools well, I do not mean spend 10 years researching a tool before you start development. I just mean tools you use are just code written by people just like yourself. So if you encounter a problem or if you see it misbehaving, spending extra time to get to know it a bit better, like maybe reading a bit more documentation, going into source, maybe contacting the community and understanding what is really happening below the HUD is actually a very good idea. And we are probably at the best point in time for that, because a lot of software we use today is open source, so you can easily even build it yourself, even debug it. So great time for reverse engineering tools you use. And the second most important under know yourself, and like, this is the most important thing I'm going to say during this talk. If I had to pick what I would like anyone to remember, this is test your solution under the expected load. So as I mentioned earlier, a lot of people say we have designed it for any scale. And then I ask, well, have you tried it like under any load? And they usually didn't. And basically, if you say it's designed for any scale, that means that you can throw any load And until you do that, you cannot say it actually works. So saying the software is built for any scale is basically impossible. Like even Netflix had a couple of days ago problems with a massive event when the fight between Tyson was, and they know how to do those problems. Like they're probably the best people in the world when it comes to scaling out your solution. So basically pick some number and test for it. And if you need more, test for it, but have a number with which you feel comfortable about running your system. So let's look at the tool we'll use a bit more today. VeloxDB. It's the database I have been developing for 2 years with 2 colleagues of mine. So technically, the database would be considered object relational database. Under the hood, the database is very similar to relational databases. It has tables, it has relations, and everything you would expect to see in a SQL database, but the interface it provides is actually object-oriented, something fairly similar to object relational mapper. It's basically as if we took object relational mapper and relational database and merge it into one solution. The database part and everything in the database is actually built from scratch by us. We do not use any existing engine for storage or replication. It's completely novel solution. It's all written in C#, but the most important parts, high performance parts, are written using unsafe C#, and it's more similar to using C than C#. So the database itself is built with 2 goals in mind: for performance without losing correctness. And that's basically how we came to the object oriented interface. Our goal wasn't to build an object oriented database. Our goal was to build a fast database, and object oriented interface is something we picked along the way as a way to interact with data and not lose performance. So it can achieve 2.5 million write transactions per second. It is fully ACID because, as I said, correctness is very important to us. So basically, when all transactions are atomic, all transactions are consistent, we have isolation, and isolation is serializable. That's the highest level available in ACID, and we are also durable. So when the transaction is done, when the database says transaction is completed, all the data is synchronously saved on the disk. We have serializable isolation. That's the highest level. I'll go into that a bit more. It's cross-platform. It can run on Windows and Linux. It's open source under MIT license. It's fully available on GitHub. There are 2 features that are not open source. Those are high availability and read scale out, but everything else is open source. One more thing it's important to note: the database is designed in such way that it expects all the data set to fit in RAM. So that's a big difference compared to traditional databases. It will work if you have like larger data set than available memory, but it will not have this performance. So if you have 16 gigabytes of data, you should have more than 16 gigabytes of RAM. And in this case, we are solving, that's not a problem. We do not have a large data set, but there are cases, of course, when you have terabytes of data, and VeloxDB is not a good fit there. So here's an example of how you define a model with the VeloxDB. Everything is done in C#. Basically a classic C# class, a bit more verbose than what Entity Framework does, but there are reasons for that. Like you implement an abstract class and describe your model with that. And what VeloxDB does is at runtime, it subclasses dynamically the class, generates code at runtime, and implements these properties in such a way that accessing a property basically goes directly to the data. So you get a very fast access to data. And how do you use this model? Well, using the model is used from something we called database operations. It's actually very similar to store procedures in traditional SQL databases, but it is written in C# instead of SQL. So let's have a look at one database operation. It's a standard C# method. The first argument it receives is always object model. Object model is basically VeloxDB's API. Using object model, you can access the data in the database. You can insert data into the database, query, access indexes, and other things. So here's an example that inserts tickets into a database. This should be done like before the concert, where you insert empty tickets that need to be sold. And it receives the number of tickets it needs to be insert during the initialization, and it just runs in a for loop. Using object model, it creates a new ticket, initializes its variables, and exits. So this one method, this database operation, is basically an AC transaction. If something happens during its execution, if it, for example, fails, none of its changes will be applied. When it succeeds, it is fully committed, and it means all the data it written is already on the disk. It is completely isolated, meaning if you have multiple transactions running at the same time, it will not see effects of any of them. And the database guarantees that it will be executed in the correct way. It is also consistent, like we support a couple of traditional guarantees like referential integrity, like if for some reason it tries to validate something for referential integrity, transaction will not complete successfully, or like if it tries to insert something into database that will violate like unique index, it will also not succeed. So one more important thing to mention about these operations is they're executed within database. Like you write your C# code, compile a DLL, and then deploy it into the database. So the code executes very close to the data, and that's one of the reasons we have great performance. And these methods, these operations are called from the client code using our protocol. It's a binary protocol designed for very fast operation. And using that protocol, you call these methods similar to like how you would do in some standard remote procedure call framework. So I would like to mention a bit more about serializable isolation because it will be important in the later parts of this talk in how it will help us implement the correct solution. So serializable isolation is basically I part of the ACID isolation. It basically says how our transactions are isolated from each other, and it's the strongest level of isolation. It basically guarantees that all transactions they have executed have a serial order of execution. Basically, a database has decided if you were to repeat these transactions in this order, you would get the same result. The simplest way to implement serializable isolation is to have a lock, like global lock that locks everything and executes one transaction at a time. But of course, this is slow, and VeloxDB does not do that. VeloxDB basically executes transactions in parallel and use something that's called optimistic concurrency control. PostgreSQL also does it that way. MicroSQL can also do it that way, but you can pick with MicroSQL if you want optimistic concurrency control or locking. And it basically what it does is it executes all transactions in parallel. And if it notices that multiple transactions are in conflict, basically that they touch the same data and that they would violate serializable isolation, it rollbacks one of them. The database would then automatically retry the rollback transaction, and it would pass because the transaction that was in conflict is done. This basically gives us everything goes in parallel, but if there's a conflict, then we will serialize the transactions that are in conflict. And here's an example I like to present about serializable execution and isolation. So if we imagine a database where you have like balls, you have modeled a table of balls where each ball can be either black or white. And we have like, for example, this situation in the database mix of black and white balls. And imagine we have two transactions, T1 that scans the table, and if it sees a black ball, it flips it to white. And T2 that does the opposite. If it sees a white ball, it flips it to black. And if you execute them serially, no matter the order you do, the end result is always going to be one color, single color database, because the first one is going to equalize all balls, and every subsequent one is just going to flip everything. But if you execute them in parallel with a database that is not serializable, that is using a weaker resolution level, like snapshot or anything lower, you can get something like this. Because this transaction starts and sees all the black balls and flips it to white, and this transaction starts and sees all the white balls and flips them to black, and each commit the balls they have changed, only the rows they have changed, and it looks like there are no conflicts because none have written the same data, but in the end we get a result that is basically impossible under a serializable execution. There is no sequential order of transaction that would produce this result. This basically happens because the database does not detect conflicts between writes and reads. Like if one transaction writes something and the other transaction reads that data, they're in conflict. They cannot be allowed to proceed together. So let's look how we use this tool to implement the problem I have mentioned. So one of the thought experiments and approaches I like to use when implementing a solution is just to give it a thought, how would such solution be implemented if we had a system with infinite resources? Like imagine if we had infinitely fast CPU, infinite amount of RAM, infinite bandwidth, like nothing to worry about. And the system, when you design it for hardware like that, it has two features. It usually has perfect correctness because you do not have to think about correctness. You can like use a lock or whatever you do, like performance is not an issue. So you can do whatever you want to guarantee correctness, and usually has a minimal complexity because you do not have to increase complexity to solve performance. And this is a nice starting point because it often reveals problems you will have when you try actually to load performance onto that system. How would this system look designed for infinite performance? Like the simplest way would be to like have a single counter, and like when someone buys a ticket, you decrease the counter when the counter is 0, all tickets are sold. But that approach does not allow us to meet all our requirements because user cannot choose which ticket then. So we have to be a bit more complex. And for that reason, we have to model each ticket as a record in a database. So user fetches all available tickets, sees which one he likes, selects it, and buys it. And that's basically it, a very simple system. But looking at this system, we can make like two important observations. Like design where we fetch all tickets is extremely expensive. Like if we have 100,000 tickets and 50 million users, if each one was to read 100,000 tickets, it would be extreme amount of data, both for moving through network and of course for querying the database. So that's something we have to solve somehow. And the second interesting one is even with infinite resources, buying ticket is inherently eventually consistent problem. User can't be part of transaction. Why? Because if you put a user into transaction, like a user comes and sees all the available tickets and then picks one and then finishes the transactions, that basically means that no other user can buy tickets while the user is buying a ticket. You basically make it serial so that every user gets an exclusive slot to buy a ticket. And when you have 50 million users, that will never complete. Even with infinite hardware, because humans are the slow part of that system. So you have to allow them to do it in parallel. User sees what tickets are available, and when they pick a ticket and try to buy it, there's a chance that someone in parallel chose the same spot. And in that case, of course, they will not be able to buy it. But it's important that we cannot escape this eventual consistency, even with strict serializable database or infinite resources. So this is like a very basic architecture. There's nothing very special because all the data, all the logic is in the database. We basically don't need much in the system except like web servers to serve our API, which are basically they basically do only protocol translation from HTTP and like some REST API to VeloxDB's protocol, nothing else. And since APIs are fairly scalable, we can have a lot of these, and we would probably need a lot of these because processing HTTP is also resource heavy job. So in order to first solve the first problem with tickets, we will not send our users 100,000 tickets. We will divide them into groups, and it even makes sense from usability point of view because user will not be picking one from 100,000. It's even hard to present user with 100,000 empty seats and to pick one. We'll divide them into groups like 1,000 tickets each group. So user first picks a group and then gets 1,000 tickets and picks one from that. And to make it even a bit more optimal, we do not need to send user the tickets that are already occupied. We'll just pick tickets that are currently available. And in order to make this even a bit more optimal, since we are already eventually consistent, since user will first read his 1,000 tickets, we can do it in a better way. We can make a special cron job, like something that's scheduled to like execute once in every second, that will scan all tickets and then build these groups. Say in this group we have 15 empty tickets, in this group we have 100 empty tickets, and this will make it a lot even less data for the user to scan in the database when they connect and try to get what are available tickets in the database. So this is an example of how the reserved ticket operation looks. So basically we have two operations. The first one is, let's see what tickets are available for the group. That's a simple read transaction. In VeloxDB, you have to first specify if your transaction is read or read write, and that allows database to optimize it a bit. Like when you come with a read transactions cannot be in conflict with anything because they are not writing. They get a snapshot of their data, they read what they want, and then they go out. So we basically do this in two transactions. The first one reads all the available tickets, and the second one attempts to reserve one. And this is an example of that code. We are using a hash index because in VeloxDB, all objects, all tables basically have a mandatory ID, which is 64-bit. And that's not very useful for tickets. It's okay for references and everything, but like tickets are usually numbered. So we are using an index to have nice numbers for tickets. And this is basically how you use index with VeloxDB. You fetch index from object model, and using that index, you fetch a ticket with a number. Now we check if that ticket exists in the database, because it's possible that some malicious user maybe entered some ticket that actually does not exist, and if it doesn't exist, we end the transaction. But if the ticket exists, we check if it's already bought. If it's already bought, we return false and transaction ends. And If we have survived this, that means that we are lucky and we have our ticket. We set its availability to false and return true, basically meaning we have acquired the ticket user asked us to acquire. So what happens when this runs in parallel? Like if you have 100 of these transactions running in parallel trying to get the same ticket, they will be in conflict because one of them will manage to write. Like if they start at the same time, you will have like imagine two transactions. Each of them sees that the ticket is available. Each of them writes false. And when they try to exit the transaction, the database will see both transactions have written the same object and they're in conflict. And it will roll back one of those transactions. So one will complete successful and return to the user. The other will be retried. And when it retries, it will start with a new transaction and it will see in the database that the ticket is actually now taken and it will return false. So you do not have to think about consistency here because database guarantees it. But what we did with splitting the transaction into two parts, that's the place where you have to be a bit careful. So how do we test this solution? So we actually wanted to test it with Azure's load testing solution that basically use JMeter under the hood. But since we were a bit time limited, we basically focused on the testing the database part and did not test the HTTP part. Hopefully, if there's some interest, like I might do the rest of the solution with HTTP and maybe publish a blog later, because building a large HTTP solution is also interesting. But we have basically focused on simulating this part of the system. So imagine we have multiple of these servers. They have all accepted connections from the clients and have their tickets they're trying to get, and they are going through this protocol. So we are going straight to the database, and database is usually the weakest point in the highly performance system. So if we can get the database to serve the clients fast enough, we can probably build the rest as well. So we have a client simulation that basically starts millions of clients. Each of them randomly picks a ticket group, fetches available tickets in the group, and attempts to reserve a random available ticket. If it succeeds, it ends because it's a happy customer. And if it doesn't succeed, it repeats the process until it either gets from the database that there are no more groups with available tickets or manages to find another ticket it likes. And we run this simulation until all clients have either bought the ticket or have given up because all the tickets are sold. We also track for each client which tickets it has acquired. We use that later to verify correctness because no ticket should be sold to more than one client. So we basically scan the logs and see if each ticket has been sold only once, and also check if all the tickets have been sold. And we also monitor when clients give up when all the tickets are sold, so we can track like how long were they trying to get tickets. This has been tested on two Azure D16 virtual machines, both with 16 cores. In a realistic scenario, I expect we would need a lot more for the HTTP layer, and probably it would be a good idea not to use pure REST and JSON, but some faster protocol that relies on binary coding data and does not parse text to get its data. So, and these are our results. This is basically how fast the tickets have been sold out. And you can note that tickets have started selling out at 7.5 seconds after the test has been started, and by 8 seconds they have all been sold. And you can also note that the speed with which tickets are sold decreases a bit, which is a bit expected, because as the number of tickets becomes lower and lower, so does the fight for tickets gets bigger, and the last tickets are the slowest ones to go. But all in all, like only half of a second before all tickets are sold. And this is all clients, all 50 million of them, how long it took them to be done with the whole process. And in 250 seconds, we have processed all clients, which is not bad. That's basically 4 minutes. After 4 minutes, everyone has bought their tickets, and most of the people are left without tickets, because that's how many there are. So, couple of takeaways. Like, always design with performance requirements in mind. Pick a number what you are designing for, and always test with that number. And know your tools. Basically, understand what's happening under the hood. So I think I've gone through my presentation a bit faster, but that means more time for questions. So any questions? Okay. So object relational database differs from other kind of databases. First, it's currently a NoSQL database, although, as I said, under the hood, it's still relational, and we're actually working on SQL engine. We plan for now to build a SQL engine only for reads, basically select only, because SQL is superior when it comes to ad hoc queries. And you often need to basically, yes, I'm looking at Discord. You often need to basically query your data to see what's happening, and maybe to provide users with some custom queries. And so that's basically the API. It's object oriented. In many ways, it's very similar to traditional SQL databases, but it's a bit faster than like what Postgre and Microsoft and Oracle and other traditional disk-based databases offer. We like to say that we have similar performance to like Redis, but with better correctness guarantees than Redis. So does this database require more RAM compared to other databases, since it's storing all the data in memory? Yes, so you need more RAM because we are expecting everything to be in memory. The reason for that is mostly because traditional databases use B trees and various types of trees for, sorry, I have not read the question. Okay, I apologize. So the question is, this database will require more memory as compared to the other databases, since it's storing all the data in memory. It's not for the large data sets and only for the smaller sets. So yes, that's the assessment is correct. Like, we are not a good choice if you have terabytes of data, but like hundreds of gigabytes of data are okay. And there's one more thing that I started to explain why we expect all data to fit into RAM. Traditional databases usually use trees as their structure for storing data, and trees are great because it allows you to group data into pages. So when you query data, a page can be either in memory or on the drive. But there's a faster mechanism for accessing data, and that's basically hash table. But hash tables are very bad for persisting on disk. And since we were chasing performance, we basically picked hash table as our key structure for storing data. And that's why we expect all data to fit in RAM, because if not all is in RAM, hash tables perform very poorly in those cases. But like, there's a lot of RAM available these days, and plenty of cases can be solved with 128 gigabytes of data set or 256, like basically up to terabyte, it's solvable. You can even go to 24 terabytes of RAM, but that's fairly expensive. And we are not targeting, of course, those cases. We are we are mostly targeted for systems that are basically doing with real-time data, processing a lot of data, doing some transactions, some conclusions, and then letting the data go, not piling the data, not storing the data or doing some analytical workloads on the data, on the huge amounts of data. So the third question is, will this eventually be distributed as a Docker container? So there is a Docker container version of VeloxDB. I think it's not the latest version, we need to update it, but you can find it on Docker Hub. And if you want to try VeloxDB, you basically do not need a Docker or any installation. Because VeloxDB is basically bundled with Nugget package. You basically start building a class library and add VeloxDB Nugget to your project, and when you hit run, it will execute your code straight into a VeloxDB. So very simple way to get started, even easier than spinning up a Docker container. For deployment, of course, there's Docker, and you can also manually deploy it on premise. And I think that answers the third question. The fourth question, are there any metrics available how VeloxDB performs compared to SQL Server or PostgreSQL? So we cannot publicly compare ourselves to SQL Server or Oracle Server because there's a part of their end user license agreement that basically says if you are going to compare, to build a benchmark against our database, you need to get our permission to publish results. But there is a benchmark available on our website comparing us to PostgreSQL. It's a fairly simple benchmark that simulates Uber-like application, basically tracks millions of vehicles and rides. And in that use case, we are like around 50 times faster than PostgreSQL on the similar hardware. The whole benchmark is open source. You can run it yourself. And the information with which we acquire this data is also available. And the part with that closing end user license agreement is actually fairly interesting. If you have time, go look it up a bit. It's an interesting story. It goes all the way from 80s and Oracle, but I'm not going to go into that. And the last questions is, what features will arrive next in VeloxDB? So we are currently working on SQL engine, and we hope to have that in like next 4 or 5 months. And we are very open to suggestions about what features you would like to see. Like, our current goal is basically to see what people like about VeloxDB, what they don't like. If someone could start building some toy projects, stars on GitHub, a bit more community traction is what we are looking at this point. So feedback on what we should add next would be very interesting. Let's see if there are some new questions that have arrived in the meantime. I'd like to address this one. So Zimenak, or if I mispronounce it, I apologize. It's a good concern. Like, unless you somehow manually move older concerts to another DB, your memory usage will just keep growing until there is physically no, no, of course, available memory. And yes, that's a very good concern. That's also one of the features we would like to add. We would like to add something similar to archiving, like an easy way to just put a huge amount of data onto a drive and say, I will not be changing this data anymore. And this data will be a bit slower to access, but because it's not in the disk. But the most important change will be that we will consider it immutable or very hard to change. And that's a feature we believe would maybe allow a lot more use cases to be used by VeloxDB, because a lot of use cases have a small chunk of active data and a huge tail of data they have just piled out. And we would probably like to address that. As it is now, you would probably be better off like archiving your data to some other solution that's using disk traditionally. Which network protocol do you use to transfer data in which format? So it's our own custom protocol. It's completely binary, and it's basically a TCP connection. It can be encrypted with OpenSSL if needed. And it's built for speed, as most things in VeloxDB. Like we support multiplexing over a single connection. So like this example you saw where we handled 50 million users, that's basically over, I think, 16 connections at the same time. We're also looking, once we add SQL, we are hoping to add PostgreSQL protocol, because it would allow a lot of existing tools to be used with VeloxDB, and it's open and fairly easy to implement. So Pedro's questions, how do you plan to establish persistence and recovery? So I might need a bit more clarification. Do you mean like backup and recovery functionality, or like hard drive persistence? So for backup and restore, we currently do not have a tool that would do that. We plan to add it. I do not know about the time frame. In the meantime, you could build your own solution that basically opens the transactions, read everything, and stores it to drive. But of course, that's a workaround. As for persistence, like we have a full persistence that basically works like with most databases. We have a write ahead log, and transactions write into that log while you're changing data. It basically, when you change something in those objects, it basically stores those changes in memory, and then in parallel puts it into a log. And we periodically also collect the log and create a snapshot, so that log doesn't grow into crazy sizes and becomes unmanageable. So we have a full persistent engine that is fully ACID, and we basically guarantee if the transaction is done, all your data is on the drive in the log, and it cannot be lost. So I think the last question, if the server restarts with all the data, will all the data be lost? No, it will not be lost. Like our main, like one of the features of VeloxDB is that it's very correct, and all the data will be on the drive. If server is restarted, it will go to the drive. It will first load the snapshot and then apply the whole write-ahead log on the snapshot, and all the transactions that have successfully passed before the server is restarted will be restored and back in memory. Also, we have support for high availability cluster that is not currently in the open source version, but it supports, like, when you complete a transaction, all your data will be on the drive of your primary node, and the second node will also have accepted the data. So we basically guarantee that you need 2 failures to lose data. If you're running high availability cluster, you need 2 hardware failures to happen for you to lose data. And by losing data, I mean transaction that has been confirmed to the user. If we said transaction has passed, you need basically 2 failures for you to come into a situation where you do not see your data on the server. What was your main motivation to start VeloxDB as a company? So we basically thought that there is a niche in the database market for high performance databases that do not lose correctness. Like, there are plenty of databases that can achieve performance, but they achieve this performance usually by sharding. And when you shard, correctness becomes very hard. Like, what happens when you have a transaction that spans shards? And a lot of databases solve that by lowering their guarantees, sometimes even not documenting them. But we wanted to try a different approach. We wanted to try to build a database that achieves best performance without sharding. And it seemed like a very fun problem. And, like, what's the point of programming if you're not programming something fun? So I'd say our main reason was for a challenge. It seemed like an interesting challenge. So it does store the data in the disk as well for backup. Yes, the data is stored on the disk. The last current question, I missed the talk. Any thoughts on publishing an implementation of iDistributed cache and use it as a key lookup store? So yeah, we could build an implementation at VeloxDB, would be a fairly good key lookup store. And you could even use it for more because it offers stronger guarantees and better transactions than traditional key lookup stores. But, like, it's, for example, a solid fit for building distributed locks, and there's a nice .NET library on GitHub for distributed locks. We wanted to implement VeloxDB backend for that, and we probably will when time allows. Hey, Simon, thank you for the suggestion. All right, and thank you, Brainiac, and everyone on the server. It was very fun. See you around. If you have any questions, you can reach me on Discord, or of course, mail and LinkedIn are in the presentations. Bye, everyone.